Okay, so we're going to go ahead and take a look at kinematics. And specifically, we're going to be interested in the case of motion where the acceleration is equal to a constant. Now, this constraint is super important to keep in mind. There are a couple of typical situations that you'll run into where this doesn't happen. An extreme case would be, say, when you launch a rocket, because as the rocket burns its fuel, its mass changes. That causes its acceleration to change as a function of time. That gets very hard to analyze and is beyond the scope of this class. Another possibility, though, involves things like, say, I go and throw a ball and then I catch it. The act of catching it causes it to have a massive acceleration pointed the opposite way of how the ball was coming in. So you have to take a little care there. In a situation like that, the usual trick is to look at the motion just before you catch the ball. Another possibility can be things like, say, you have a situation where a car accelerates at a constant rate and then it slams on its brakes. In a case like that, what you can do is you can actually split the motion into two parts. You can first do it while the car is being constantly accelerating as you're stomping on the gas, and then you can analyze that bit, get what the final position, the final velocity of the vehicle is at that point, and then you can use that as the initial values for the second part where you're going ahead and stomping on the brakes. So anyway, the main point here is that the relationships that we're going to come up with are only valid if the acceleration is a constant. If it's not, if it's at least pieces that are constant, we can kind of patchwork the pieces together. If it's just not constant at all, you need to use the methods of calculus, and that's beyond the scope of this course. So with that aside, let's go and remember what our definition of acceleration is. Sorry about that. Acceleration is defined to be, that's the little triple equal sign, the time rate of change of the velocity. So the change in velocity over the change in time. Well, remember, the change in anything is the final value of that thing minus its initial value. So v final minus v initial over delta t. Now here, since the acceleration is a constant, this is no big deal. We can rearrange this to solve for v final. And so we get v final equals v initial plus the acceleration times delta t. Now, a little bit of care should be taken here. Strictly speaking, I should be saying Vx final, Vx initial, Ax, because we're taking a look purely at one-dimensional motion. So I'm just noting along the x-axis. If it was the y-axis, we'd make these all y's. Okay. Now, this turns out to be, this turns out to be one of our, what I'd like to call, the gang of four kinematics relations. There are four super useful relations, so this is the first of them. Let's go ahead and come up with the second of them, and then the third and fourth will follow. Alright, so now for the second one, let's think about what it means, what a typical velocity time graph would look like. There we go. Velocity time for constant acceleration. We've already seen that will look like some sort of a straight line. Now, it could be below the time axis, it could be above, it could be slanted up, like I've drawn it here, it could be slanted down. It doesn't really matter. All right, so let's say this is my initial time, and that's my final time, t final. All right, so we've already seen that this area right here that I'm cross-hatching in blue, that this is the displacement. Delta x. All right, so we can use that. So delta, so our displacement will be equal to this area right here. This is the area of a trapezoid. So this says that the displacement, delta x, will be equal to the area of this trapezoid. So we'll just say AUC for area under the curve. So that is equal to, the area of a trapezoid will be 1/2. All right, the height of this right here is going to be my Vx initial. The height of that right there is my Vx final. So I have to average those two heights. So 1/2 Vx initial plus Vx final, and multiply it by the depth here, delta t, because this is t final minus t initial. So that makes this width right here equal to delta t. Okay, so we're pretty close to the usual way this gets written. The main thing to note here is that the displacement is the change in position. The change in anything is the final minus the initial, so x final minus x initial. So the usual way we write this is we add x initial to both sides and write this as x final equals x initial plus 1/2 Vx initial plus Vx final delta t. All right. Now to get the remaining ones. To get the remaining ones, we can first look here. I've got this expression here for Vx final, right? I could go and put it in for Vx final there and just get rid of Vx final. So let's go ahead and do that. So plugging into that, so x final equals x initial plus 1/2 Vx initial plus, now my Vx final we're going to write as Vx initial plus Ax delta t. That's all inside the parenthesis, and then we still have a delta t outside the parenthesis. All right, so this much here is going to be 2 Vx initial. When I times it by 1/2, I'll just be left with Vx initial delta t. So I got x final equals x initial plus Vx initial delta t plus, now I still have a 1/2 Ax delta t, and I times it by another delta t, 1/2 Ax delta t squared. Okay, this is another one of our gang of 4. All right, now to get the remaining member of our gang of 4, instead of eliminating Vx between our first two relations like we did before, what we'll do instead is we'll take this guy, solve him for delta t, stick that solution into here, and then come up with a new expression. So let me go ahead and make it a little easier. I will copy this. And paste it over here. Perfect. And just to remember what we were talking about here, I will go ahead and copy this guy. And bring him in here too. Great. Okay. So now I'm going to take this first guy here. Oops. I'm going to take this first guy here, and I'm going to solve him for delta t. So we'll subtract Vx initial from both sides. Then we'll divide by Ax, and we're left with delta t. And then I'm going to take my value of delta t there and substitute it in over here and see what we get. Okay, so we have x final minus, I'll subtract x initial from both sides just to get this heading into a standard form, plus 1/2. I'm going to commute these two, so vx initial plus vx final, same difference as vx final plus vx initial. Then I'm going to put in my delta t. My delta t is vx final minus vx initial over a sub x. All right. So if I go and take a look at this bit here, well, actually, let me take care of this bit here first. This bit here is just delta x. And then what I'll do is I'll get rid of both of these denominators and multiply through by 2ax. Okay, great. Then what I'm left with is just the two things in parentheses. And if you remember that from algebra, that's going to be vx final squared minus vx initial squared. When I times those two together, the cross terms cancel. Okay, the usual way we write this is to say vx final squared minus equals vx initial squared plus 2a sub x delta x. Okay, so that's my fourth member of my gang of four. So let me go ahead and put them all together in one spot, and then we'll discuss it a little more. So first we've got this guy. So we'll copy, let's start a new page here. Paste. And then the next one I want is actually going to be this guy right here. Copy, paste. There we go. Then the next one I want is the second one we ever, whoops, sorry. That's the third one I want right there, my bad. All right. The second one I want is actually the third guy I came up with right here. Copy, paste. And then the fourth one is this last one that we came up with. Copy, paste. All right. So now if you look at these relations, I want you to notice that there's, I want you to notice that there's something missing from each of these. In this first one here, if you take a look at this one, there's no x. So we're just missing x. This equation here, we have an x, we've got a v initial, but no v final. We have an a, we have a t. So this one is missing vx final. Similarly, oops, how to do that? There we go. Similarly, this one here doesn't have an a in it anymore. There's no acceleration in that relation. And this one here is missing the time. Okay, I like to call these four the gang of four. And a lot of textbooks, yours included, only give you the first three. And actually that's okay, because as you saw, if you have any two of them, you can come up with the other two. A lot of books choose to only give you 3 of them because there's sort of a special thing that happens if you've got all 4 and you're kind of derping around playing with stuff and you keep substituting different things in. You can eventually get to a situation where absolutely everything cancels. You're left with 0 equals 0 and you don't have a solution. But the trick here is if you pay attention to what's missing, you can use that to directly figure out which of the 4 kinematics relations you want to use for your problem. So let's go ahead and do a couple of sample problems here. But before we delve into that, I just briefly want to get into my favorite mnemonic for remembering how to solve any kind of a physics problem. The mnemonic is STAR. Stands for situation, tools, answer, review. So the first thing you need to do is understand your situation, and every physicist, it does not matter if they're doing a kinematics problem or they're doing some sort of hyperconvoluted string theory stuff, the very first thing they will do is draw a picture. The act of drawing a picture does a lot to help you visualize it and understand it. Within this, you will then try to understand what you are asked for and what you are given. Once you understand the situation, then the next thing you do will be to identify the tool you need to answer the problem. I do not recommend, in fact, I strongly recommend against diving through the book looking for random equations that look like they have the right letters. A lot of equations in the book are for very, very specific situations. It's best if you start with things that are very general. For instance, this gang of 4 here. Or, equations that are named after people are usually a pretty safe bet. Equations with very pompous sounding names, generally very safe bet. Start with things that are always true. Apply it to your situation. So in this case here, we'll use identify which of the kinematics relations we want by identifying the missing variable to select the appropriate relations. Okay, this much here is physics. That's physics. The answer part really is mostly math. Do not put in any numbers except for 0. And solve for the thing you want on the left-hand side, everything else on the right. So this is just mostly doing a bunch of algebra. At the end, though, put in your numbers with their units and get a final answer. And then review it. A couple of things that you should be checking are, does it make sense? If your answer has a baseball spontaneously flying up, you probably made a mistake. Also, really big deal is, at the very least, make sure you check your units. If you are solving for a velocity and you get something that's meters cubed over seconds to the 5th, you made a mistake somewhere. Okay, so with that in mind, let's do just a couple sample problems and try to get a handle on it. So I'm just going to do a couple here. So the first one I'm going to look at, we'll say we have a car. So I'm going to go ahead and just start drawing my picture right now to understand it better. We have a car initially moving at 100 meters per second. So the problem says initially moving 100 meters per second, so Vx initial equals 100 meters per second. When the driver hits the brakes, causing it to decelerate at 20 meters per second squared. Ooh, that word decelerate was a little tricky there. If if we're decelerating, that's really telling us that the acceleration is pointing in the opposite direction of the velocity. I arbitrarily chose my car to go to the right, which is positive. So that's now forcing me to identify the acceleration as being minus 20 meters per second. And the minus sign there is because I'm going to the left. And then so now here's my car over here. And then they say, okay, after 2 seconds, how far has the car moved? So they want to know the distance traveled, and they are willing to tell you that 2 seconds elapsed to get to that point. Okay. So now I understand my situation. I am being asked for the displacement, delta x. I have been given the initial velocity, I have been given the acceleration, and I've been given the elapsed time. So to identify my missing variable, and I always put missing in quotes because we can find it if we want it, I am missing v final x. All right. So I know I'm missing v final x. I can go back to my gang of 4 and say, oh, this is the guy that looks like he'll do the job. So let's go ahead. Copy. Paste. And we'll get rid of the box. There we go. So this is my starting point here. All right. Now, they were a little annoying to me. They asked for the displacement, not the final position. So what I'll have to do is I'll have to subtract the initial position from both sides. Oops. X final minus x initial equals, well, hey, that is the displacement. Yay. And then I'm left with what's left, Vx initial delta t plus 1/2 ax delta t squared. Oops. All right. Gack. Sorry about that. All right. So we'll go ahead and put in my values here. So delta x equals, they told me it was initially moving at 100 meters per second. The time elapsed was 2 seconds plus 1/2. The acceleration we said was negative 20. You got to put in that minus sign. Meters per second squared times my 2 seconds squared. Now when I square this, I'm squaring both the 2 and the seconds. All right. So let's go ahead now. On our way to getting our answer, we can sort of be checking our units while we're at it. I'm expecting this to be in meters because it's a displacement. Meters per second times seconds. The seconds will cancel. Great, I'm left with meters from this term. So that's 200 meters there. And then let's see, this is going to become 4 seconds squared, and the seconds squared will cancel against those seconds squared. Great. So I'm left with meters. That's good. 2 times 20 is 40. Negative 40 divided by 2, negative 20, right? Yeah. So, wait, 2 times 2, 4, 80. Sorry, negative 80 divided by 2, negative 40. Minus 40 meters. Now, when you add or subtract things, the units have to be consistent, and they are. Super. 160 meters. A little over 2 football fields, a little under 2 football fields. Yeah, that sounds about right. So the review checks out, and we get that we displaced 160 meters. Okay, let's do one more example of how to do this sort of thing. Let's say we have a car slows down. All right, so we'll draw a car. car slows down from 100 meters per second, v initial x equals 100 meters per second, to 40 meters per second. Okay, so they're giving me the final velocity there. V final x equals 40 meters per second over 100 meters. So they've given me the displacement. Delta x equals 100 meters. What is the acceleration? All right. So I'm asked for the acceleration, I'm given the displacement, and I'm given the initial and final velocities. What I'm neither asked for nor given, so it's my missing variable, is the time elapsed. All right, so the missing delta t equation, oops, sorry about that. Gag. There we go. So the missing delta t equation, remember, is Vx final squared equals Vx initial squared plus 2a sub x delta x. So yeah, I should say a sub x there. All right, now it would be so I've identified my tool. It would be very, very tempting at this point to go stick in the numbers, but really, really, really resist the temptation. What can happen is you can start to over-round. And once you start putting in the numbers, what tends to happen is each time you round, it takes your answer away from the right value. And I've seen it sometimes where people have been off by literally, 30-40%, having done it mechanically right, but just the rounding took them that far out. That's one of many reasons to resist putting in the numbers. So we're going to resist putting in the numbers. We're being asked to solve for a sub x. So we're just doing math here at this point. The physics is kind of done for a moment. All right, so 2ax delta x is going to equal vx final squared minus vx initial squared. I want to get my ax, so I'm going to have to divide by 2 delta x. Ax equals vx final squared minus vx initial squared over 2 delta x. Okay, now I've got what I want on the left-hand side and everything I'm given on the right-hand side. So the final velocity is 40 meters per second. I'll be squaring that, minus 100 meters per second. I'll be squaring that, over 2 times 100 meters. All right, do the numbers make sense here? Well, the units are consistent here, so that's at least good. When I square this, I'll have meters squared over seconds squared in the numerator. Same with that term, so the units in the numerator are that. I just got meters there, so yep, meters per second squared. Yeah, that looks good. All right, great. So my units are going to make sense. Let's go ahead and get the number. So 40 squared, 100 squared minus 2 divide, 100 divide. Okay, negative 42. All right, so we get negative 42 meters per second squared. All right, so let's review. The units check. That's good. We had an acceleration, and we got the right units for acceleration. That's good. The car was slowing down, so since the velocity was positive and the car was slowing down, we expect the acceleration to be negative. So the acceleration is pointing to the left. That makes sense. And 42, okay, he's really slamming on the brakes really hard. We're looking at race car kind of decelerations, but it is kind of possible, so I guess we can go ahead and roll with it, especially since your instructor is a big fan of the Hitchhiker's Guide to the Galaxy, and the number 42 is really awesome in that book. So I hope this helped a bit, and I will catch you guys later.